the microcanonical ensemble, the relevant partition function is just omega, the number of microstates that are accessible, and the relevant thermodynamic potential of interest is the internal energy. But with the microcanonical ensemble, it's typically, by definition, it deals with systems in which the internal energy, volume, and number of molecules is kept constant. But in an actual experiment, considering the fact that internal energy is something that can't be directly measured, it's not the most convenient thing to define a system in which, or think about a system in which we keep the potential energy or the internal energy constant. But rather, typically when experiments are done, they're performed at isothermal conditions. So you kind of set the temperature of your system to some value, and you do everything you can in order to maintain that temperature. Okay? And so rather than trying to describe a system in which U, V, N are the constant parameters, it may be a little bit more convenient to describe a system in which temperature, volume, and number of molecules are kept constant. Okay? And so in this sort of system, in which T, V, and N are the constant parameters, we refer to this as the canonical ensemble. So we were dealing with microcanonical before, now we're going to be dealing with canonical, right? And so let's kind of define, the relevant sort of partition functions and thermodynamic properties that are relevant for a canonical ensemble. Okay? Okay. All right, and so to develop these things, we're first going to consider the following system. So consider a composite system that has two parts. Okay? Where there's some sort of subsystem inside a large bath. Okay? All right, and so we could describe it pictorially like this. Right? Where we have our subsystem, and then we have our bath. And then outside the bath, let's say it's well insulated, so nothing else can go into this composite sort of system. Okay? All right, and the system is designed in such a way such that the volume of our subsystem is much smaller compared to the volume of the bath. Okay? And the number of molecules in the subsystem and in the bath are constant. Right? There's no exchange of molecules between the two. Okay? The total internal energy, so of the subsystem plus the bath, we'll say it's constant, right, just based on conservation of energy. But these individual values themselves can change. So the subsystem's internal energy could go up or down, and the bath's internal energy can go up or down. The sum of them is constant. And so, because of that, we could rewrite the bath internal energy like this. Okay? All right, so that's how we're going to define our system. And now what we want to do is we want to determine or develop a framework for determining if the subsystem is in some state J. So whether the subsystem has some sort of temperature or has some sort of internal energy, we want to figure out if it is in that state. And Likewise, we want to figure out if the bath is in state K. So if its internal energy adopts some other value. In order to develop this framework, what we're going to just start with is we're going to apply the principle of a priori probabilities. So just like we did with the microcanonical ensemble. Okay? All right, and so here we want to determine what's the probability that the subsystem is in state J and the bath is in state K. All right, from our discussion of a priori probabilities in the previous video, we know we could describe it like this in terms of a delta function divided by the omega that's a function of the total macroscopic internal energy. Just for brevity, I didn't write it, but volume and number of molecules is also here. But we're going to be keeping that constant anyways. Okay? All right, so we could describe the probability of this combined system like this. All right? And now, if we want to find the probability, find probability of subsystem J, subsystem state J, for any bath state. So, what's the probability that we could achieve state J regardless of the state of the bath, right? And so to do this, to get Pj, we would just sum up the probability of Pjk for all k values, right? That's all we would do. And so based on the principle of a priori probabilities, we could write it like this. Okay? Now, as we saw before, in the microcanonical ensemble, just by kind of rearranging all of the probabilities, we know that the summation of the delta function here can be related or is equal directly to n omega. In this case, it would be equal to omega of the total internal energy of the entire system minus the internal energy of just the subsystem. Okay? All right, since we're summing over all of k, that means we're just looking at the probabilities or the delta functions of just the subsystem state J. Okay? All right, and so with that, all right, here, this P sub J is going to be equal to this. Okay? All right, and so here, basically what it's saying, the probability that you're in state J is equal to, the number of microstates that correspond to this sort of internal energy divided by the number of microstates that just correspond to the entire internal energy of the combined system. Okay? All right, so that's just, how we're going to define the probabilities. And right now we're defining them in terms of the number of microstates. What we could do now is we could rewrite this ratio in terms of entropy. Because we can rewrite P of J in terms of S. right? Since we know that S is just equal to KB ln of omega, so if we have omega, that means what we have is this. And for subsystem J, I'm just going to write it as uj now. And this is divided by KB divided by exponential okay. All right, and so now we've rewritten the probabilities in terms of entropies. And I'm going to write this as equation 1. Okay? All right, and so we've exchanged the omegas for entropies. But that still doesn't really help us at this point because we don't really have a functional form of entropy that's directly related to temperature yet. Okay? And so in order to relate the entropy directly to temperature, what we're going to do here is we're going to rewrite this entropy. We're going to rewrite it by applying a Taylor series expansion. Okay? And that Taylor series expansion is going to be centered around the uj being equal to the average value of uj, right? Or in other words, I'm just going to call this u average. Okay? All right, and so that means that the entropy here can be approximated by this Taylor series expansion, where we would write it like this. Plus u average minus uj. We're taking the derivative of s with respect to uj, constant v, n, and then there are some higher order terms here. Okay, and so this is a Taylor series expansion, and the reason that doing this is useful because we have this derivative of ds du, and we know from our properties of entropy that this derivative is just equal to 1 over temperature. And so we could rewrite this entropy term as this: u total minus u average plus u average as uj divided by temperature. And I'm going to call this equation 2.